Hello guys, this is CodeNcode and this is part 2 of this Finding Bridges lecture. In this lecture we are going to see the implementation, and we are first going to take an example and see how bridges are find how we find bridges in a given graph. So this is a very basic example. I could have taken a much better example, but it actually is irrelevant. So there are two arrays which we are going to use, and first important thing, since this lecture is part 2, so I advise you to go and watch part 1 because that is the very important lecture. There I have explained about DFS tree and how the concept of back edges, forward edges, and so on, and that lecture really is really important. So if you are missing that lecture, please don't, because that is the foundation of algorithms, or the concept that we would study, and the concept that would help you solve really good problems on Codeforces or any other competitive programming website. So let's continue. We will take two arrays, in and low. In would store the time at which you enter a node. So initially it is 0, so when we made a DFS call to node 1, so in of node 1 would be 0, and then suppose from there you went to 2, so in of 2 would be 1 because at time 1 you entered 2, and then in of 4 would be 3, or 0 1 2, sorry, 2, and in of 3 would be 3. So in time indicates the time at which you enter a node, and low time indicates first important thing of in time is that if two nodes lie on the same path from root to some leaf, then the node which is having the lower in time is actually the ancestor, and the one which is having the higher in time is descendant, right? So 0 1 2, you can see all lie on the same path. So 0, which is this node, is actually ancestor for both this and this. 1 is ancestor of this, and so on. So in time helps us to maintain this relation, ancestor descendant relation. Now low time is the time which indicates for each node what is the lowest ancestor which can be reached directly from that node. For node 4 it would be node 2. So low would store that information, right? So how this algorithm proceeds: first you made a DFS call to node 1. So what would happen? We would initialize the low and in time of node 1 to be 0 because timer was 0. We would now increment the timer. Now what it indicates that you entered node 1 at time 0, and the lowest ancestor of node 1 which is known to node 1 is actually node 1 itself, the node which entered at time 0, and the node which entered at time 0 was node 1. So the low of node 1 is itself. Now in the adjacency list of node 1 there is 2, right? So we would make a DFS call to node 2, and this would be marked black because this is a forward edge. So we don't actually have to mark it, it is just to show you. It is just a visual representation. It is not actually a thing we do in coding. So now we are at node 2. So node 2 in and low time would initialize by 1, and we would increment the timer. In the adjacency list of 2 there is 1 3 and 4, right? So we would not do anything for 1 because it is its parent, and now we would go to 3, and since we reach 3, so we would initialize the in and low time of 3 to be 2 and increment the timer. In the adjacency list of 3 there is 2 and 4. We would make DFS call to node 4. As soon as we reach node 4, we would initialize the in and low timer of node 4 to be 3, and we would increment the timer. Now this is interesting. Now node 4 has two nodes in its adjacency list, 3 and 2. Now 3 is its direct parent, so we won't do anything because that is already visited. Now 2, even though it is visited, but this represents, since it's not direct parent of 4, hence this represents a back edge, right? A back edge indicates node 4 is connected to its ancestor, and hence the low time of node 4 would change. load time of node 4 would change by minimum of load time of 4 or in time of node 2. In time of node 2 is 1, so load time of 4 would change to 1, which indicates that node 4 is directly connected to an ancestor who entered at time 1, and the node which entered at time 1 was 2. So basically, whenever there is a back edge, the load time of that node would be updated, and load time would be updated as load time of current node is equals to load time of current minimum of load time of current node, comma in time of the that node. So how this is done, let me show you with an example, otherwise this would go overhead for most of the people including me. So what we need, we first need vector of int, the adjacency list. We are assuming there are no more than 100 for now, it is just to take an example. Then we need in array, and we need low array, and then we need visited array. After that we need n, m, x, y. There are n nodes and m number of edges. Now sorry, while m minus minus, because there are m number of edges, we would read x, y. So in the adjacency list of x, we would what is this, sorry, so we would insert y, and in the adjacency list of y we would insert x. Now the graph is completed. Now we would make DFS call to node 1 and passing its parent. It is important to pass for each node its parent, so it can decide whether the current visited edge, so in the adjacency list of 4 you see there is 3 and 4, both are visited. So how to distinguish between the node which is its ancestor and the node which is its parent? For that we need to pass parent. So since there is no parent of root, so you can pass anything which is invalid, -1, -10, doesn't matter. So we would pass -1. Node, int node and int parent. Now what would happen here, you would first mark the current node to be visited, and in time of current node and low time of current node is equals to timer, right? And then we would increment the timer. We haven't taken the timer, in timer. Since I've declared the timer to be globally, so it would initialize with 0. Now whenever you reach any node, you do 3 things. First, you initialize its in time and low time, and then increment the timer. Oh yeah, we also mark it as visited. So everything we have done. Now what we do, for each node we traverse its adjacency list and see which edge is forward edge and which edge is back edge. So in the adjacency list, I call it each node, I call it child. So in the adjacency list of current node, there are 3 cases. First, the current node in the adjacency, the current node, this child is actually its parent. This node is actually parent of current node, or this is already visited. Yeah, there are 2 cases actually. So it is also possible that this node is parent. If that's the case, we would do nothing, because if it's parent, it is already visited. So if it is visited, we won't make a DFS call, and since it is its parent, so we can't update our load time as well. So if this node is actually its parent, we can't do anything, so we would simply continue. Otherwise, if this node is visited, if that's the case, which means this is a back edge. So we were in the adjacency list of node 4. In the adjacency list of node 4 there is 3, but 3 is its parent, so we would continue. In the adjacency list of 4 there is next node which is 2, and 2 isn't its parent, and hence it have to be 2 is also visited, so it have to be its ancestor, hence it is a back edge. So if it is visited, this edge node to child is a back edge, right? Let me just, yeah, so this is a back edge, else this is a, this edge node to child is actually a forward edge, right? So now let's proceed for both of them. So if this is a back edge, then what we do, if this is a back edge, what we did, we minimize the load time of node 4. So what we do, load time of current node is equals to minimum of load time of current node, comma, in time of child node, right? I call this child, but it is actually not child, so but it's just I say. So what we do, if this is a back edge, we try to minimize the load time. Why can't we directly initialize a load time of current node is equals to in of child? The reason, when the execution of this is completed, we would track back to this, track back to node 2. In the adjacency list of node 2 there is node 4, but hence, and this is already visited and it is not the parent of node 2, so it must be a back edge, which is true, but it won't minimize the load time of node 2 because 4 is not actually the ancestor of node 2. That is why if I directly assign the load time of 2 to be equal to load time of 4, that would create a problem. So that is why we try to minimize instead of directly initializing or directly overriding the value of current node. So if it is already visited, which means it's a back edge, if it is a back edge, all we do is we minimize the load time of current node. Otherwise it's a forward edge. So when you were at node 2, when you were at node 1, we see node 2 is not visited and node 2 is not even parent of node 1, so which indicates this edge is actually a forward edge. If this is a forward edge, what we did, we made a DFS call. So that is the thing we would do. We would make a DFS to node child, and for node child its parent is the current node, so we would make DFS call to that. After that, DFS node of current node is completed, so it would track back. Now after that, what it would happen, oh yeah, I haven't explained the example completely. So we have minimized the load time of node 4, right? What would happen after that, adjacency list of 4 is completely traversed, so it would track back to node 3. Now since you are at node 3 would check, okay, since you have minimized all of your load time, now it's time for me to test whether this edge, the edge between me and you, is actually since this was a forward edge, so actually is a bridge or not. To test that, what we would do, we would simply check the load time of this node. The load time of this node should be greater than or equal to in time of 3. So since load time of node 4 is greater than or equal to in time of node 3, hence this is not a what we call is bridge. And why is that so? So see, the load time of node 4 is smaller than the in time of this, which indicates node 4 is connected to even the ancestor of node 3, which means even if you remove this edge, there is a path from root to this node, and hence this cannot be a bridge. Again, if the load time of node 4 is smaller than the in time of node 3, which indicates that node 4 is connected to an ancestor of even node 3, which means that even if you remove this edge, node 4 is still connected from another path, and hence this edge can't be a bridge. So what we are going to do, we are going to check if load time of node 4, which is actually child, it would be a bridge if its load time is greater than the in time of current node. If that happens, then call is let's simply print this no node, this is current node, and this node, the child node, is a bridge. Next line. So this is what is happening. So if its load time is either equal if its load time is greater than the in time of 3, which would indicate that okay, node 4 is not connected to any of the ancestors, and hence this would be a bridge. Otherwise it won't be a bridge. So that is why if the load time of child is greater than the in time of node, then this is actually a bridge, otherwise not. Even after testing for this whether this is a bridge or not, since the in time of this is smaller than load time of node 4 is smaller than the in time of node 3, hence this can't be a bridge. Since this is not a bridge, I'm marking it as green. After this node has tested this edge for bridge, it would try to minimize itself, because see, the reach of node 4 is to this ancestor, right? Since node 3 is connected to node 4, so node 3 can also reach to that minimum where node 4 can reach, and hence node 3 also would minimize its load time. So load time of node 3 is currently 2, which is itself, and since load time of node 4 is 1, so node 3 would update its load time for from node 4, because node 4 can reach to node 4 can reach to low of node 4, and since node 3 can reach node 4, so node 4 can reach as low as node 4 can reach. So that is why node 3 also would update its load time. So after it has tested for bridge condition, current node would also try to minimize its load time. So minimum of load time of current node, or minimum load time of this child. Since if a child can reach this minimum, then the current node also can reach this minimum because node is connected to this child by an edge. So I think this is all. Let me see. Yeah, I think this is all. Let's test this. Yeah, and mark it as test, and let's see we don't get any error. Okay, yeah, timer. This is the only error, which was a typo. So let's see. Okay, let's try to make this graph. Oh, come on. Yeah, so there are 4 nodes and 4 edges. 1 is connected to 2, 2 is connected to 3, 2 is connected to 4, 3 is connected to 4. So we see 1, 2 is a bridge. We can create let's create a star tree. So 4 node and 3 edges. 1 is connected to 2, 1 is connected to 3, 1 is connected to 4. All these edges are actually bridge. So 1 2 is a bridge, 1 3 is a bridge, and 1 4 is a bridge. So this would work, of course, because this is the way we find bridges. So what we do first, as we land on a node, so what we do, we mark it as visited, we initialize its in and low time to be timer, and we increment the timer. After that, we traverse each child in the adjacency, or basically each node in the adjacency list of current node. If that node is its parent, we would continue because we can't do anything, because that node would already be visited. Otherwise, if it is not child and visited, so it is a back edge. If it is a back edge, we would minimize our load time by the in time of that node. After that, if it is not a back edge, which means it's a forward edge, if it's a forward edge, first we would make a DFS call to that node so that that node can minimize its load time. After that, we would check for the bridge condition. Bridge condition is that the load time of child must be smaller than current node, smaller than or equal to current node. If that is not the case, then this is a bridge. So since this was a bridge, so I printed this. We can do a lot more than just printing. I was just trying to show you. And after that, current node also tries to minimize its reach to some of the smaller ancestors. So that is done in this line. So this was all for this lecture. I hope this was clear to you. If not, if there is any confusion, just post it down in the comment section. And if any suggestion, you're always welcome. Thank you guys for watching, and for the next video, till the next video drops, keep coding. Thank you.